In this lecture, we talk about hyperbolic structures on surfaces. A hyperbolic structure on a surface S is a complete Riemannian metric of constant curvature -1. This means that the surface is locally isometric to the hyperbolic plane, so that there is a developing map from its universal cover to the hyperbolic plane, unique up to isometry. Because the hyperbolic structure is assumed to be complete, this developing map is an isomorphism, and therefore we can realize the universal cover of S as the hyperbolic plane in such a way that the deck group acts as a group of hyperbolic isometries. Conformal automorphisms of the unit disk are isometries in the hyperbolic metric. This is called the Poincaré disk model. If S is a Riemann surface, not isomorphic to the complex projective line, to the complex line, or to the punctured line or a torus, then the universal cover is isomorphic to the open unit disk, and therefore S admits a unique, complete hyperbolic metric in its conformal class. In particular, every surface of infinite type admits a hyperbolic structure. Let S be a hyperbolic surface. We're going to think of its fundamental group as a group of isometries of the unit disk in the Poincaré metric, and we're going to denote it by gamma. The limit set of S, denoted lambda, is a subset of the unit circle, which is defined to be the set of accumulation points of any gamma orbit. In some exceptional cases, the limit set has 0, 1, or 2 points. In this case, we call gamma elementary. Otherwise, the limit set lambda enjoys the following properties. It is compact, non-empty, perfect, and minimal, which is to say that every gamma orbit is dense. Furthermore, it is the unique gamma invariant subset of the unit circle with these properties. Let's assume gamma is non-elementary. Then the limit set lambda has the following important property. For any 2 points P and Q, and any 2 open neighborhoods U and V containing P and Q, there is some element in the group gamma whose axis has endpoints in U and V. Let's prove this. If we choose any hyperbolic element and take its axis, then by minimality we can find 2 translates of this axis, one of which takes the attracting fixed point into U, and one of which takes the repelling fixed point into V. The conjugates of this hyperbolic element by these 2 translates are called G and H. Thus, the axis of G has an attracting fixed point in U, and the axis of H has a repelling fixed point in V. By replacing G and H by powers if necessary, we can find disjoint open neighborhoods of their fixed points with the following property. Let's call the neighborhoods of the fixed points of G U plus and minus, and let's call the neighborhoods of the fixed point of H V plus or minus. The property we want is that G takes the complement in the circle of U minus to U plus, and H takes the complement in the circle of V minus to V plus. A pair of elements and neighborhoods with this property are said to satisfy the ping-pong condition. Now, let's look at the dynamics of the element GH. H takes the set U plus inside V plus, and then G takes V plus inside U plus. So the element GH takes U plus inside itself and has a fixed point there. Similarly, G inverse takes the subset V minus inside U minus, and then H inverse takes the subset U minus inside V minus. So H inverse G inverse takes V minus inside itself and must also have a fixed point. Thus, the element GH has fixed points near P and Q. Associated to the limit set lambda is its convex hull C of lambda. This is gamma invariant and covers the convex hull C of S inside the surface S. C of S, the convex hull of S, is a hyperbolic surface with totally geodesic boundary, and the nearest point projection from S to C of S is a homotopy equivalence. The boundary components of C of S are totally geodesic. They might be circles or lines, and each one cuts off some non-compact subset of S, which is associated to a unique end of S. The map from components of the boundary of the convex hull to the ends of S is neither injective nor surjective in general. However, the following is true. The compact components of the boundary of the convex hull are associated to isolated planar ends of S, whereas the non-compact components are associated to ends which are either non-isolated or non-planar, or possibly both. Let's prove this. A compact component of the boundary of the convex hull cuts off a cylinder, which is an isolated planar end. So we really just need to look at the case of the non-compact components. Let L be a non-compact component. For any point on L, we can find closed geodesics, gamma I, contained in the convex hull of S, with points on them, P sub I, that converge to P. The gamma I are not necessarily simple, but by cut and paste, we can replace them with simple geodesics also containing points Pi converging to P. Now there are two possibilities. Either infinitely many of the gamma I are non-separating, or all but finitely many are non-separating. If infinitely many of the gamma I are non-separating, then these are all cores of handles which are accumulating the end. Otherwise, for all but finitely many of them, they're separating and they cut off subsurfaces with non-trivial topology, and these subsurfaces likewise must accumulate the end. Thus the proposition is proved. It's a useful fact that every surface of infinite type has a hyperbolic metric for which the surface is equal to its convex hull. Here's how to show this. We write S as an increasing union of subsurfaces Si, where now we don't insist that the Si are compact, but we assume that they are of finite type and that every isolated end is in one of the Si. We assume further that every component of the difference Si plus 1 minus Si has negative Euler characteristic. Then we can put a hyperbolic structure on each Si plus 1 minus Si made for pairs of pants with bounded cuff lengths. If the length of the cuffs is bounded, then there's a lower bound on the distance between distinct boundary components of each Si plus 1 minus Si, and therefore the hyperbolic structure on their union is complete. Now let's suppose we have two hyperbolic surfaces S and R and a homeomorphism F between them. The homeomorphism F lifts to a map F twiddle between the universal covers, and since the surfaces are both hyperbolic, the universal covers are both the unit disk. So we get a homeomorphism F twiddle from the unit disk to itself. We say that F has the continuous extension property if the map F twiddle extends continuously to a map on the boundary circles. This property is automatic when the hyperbolic structures on S and R have finite area. For instance, when these surfaces are closed. But for surfaces of infinite type, it's not necessarily the case that every homeomorphism has the continuous extension property. Nevertheless, the following is true. Supposing the hyperbolic structure on R is chosen in such a way that the convex hull of R is equal to R. This is equivalent to saying that the limit set of R is the whole circle at infinity. Then every homeomorphism from a hyperbolic surface S to R has the continuous extension property. Let's prove the proposition. Supposing we have a sequence of points SI in the unit disk converging to some point Q in the circle. And let's let R sub I be the images of the S sub I under the map F twiddle. What we need to show is that the R sub I converge to a unique point in the circle at infinity. Let's suppose to the contrary that the Ri have subsequences converging to two distinct points, P and P prime. Now, because R is equal to its convex hull, the limit set of R is the entire circle at infinity. This means that if we have two distinct points, P and P prime, at infinity, we can find compact geodesics gamma and gamma prime in R with lifts gamma twiddle prime, which bound disjoint intervals I and I prime contained in the circle so that P is in I and P prime is in I prime. Let's let delta be the preimage of gamma and delta prime be the preimage of gamma prime under the map F. Since these are compact curves, their lifts, delta twiddle and delta prime twiddle, are quasi-geodesic. This means that they limit to points in the circle, and these points in the circle bound disjoint intervals J and J prime. The sequence Ri has subsequences converging to P and P prime, so the preimage Si has subsequences, one of which enters the domain bounded by delta twiddle and one of which enters the domain bounded by delta twiddle prime. This means that Si has subsequences converging to points, one in the interval J and one in the interval J prime. But our sequence Si was already assumed to converge to Q. This is a contradiction, and therefore we can conclude that the image of the sequence R sub I converges to a unique point P in the circle at infinity. We can therefore define the extension F twiddle of Q to be equal to P and observe that this resulting extension is in fact continuous. A similar argument shows, under the same hypothesis, namely that R is equal to its convex hull, that if we have two homotopic maps, F1 and F2 from S to R, with lifts F1 twiddle and F2 twiddle, then the continuous extensions of F1 twiddle and F2 twiddle agree on the circle at infinity.